Good morning, class. Today we're going to talk about the characteristics of polynomials, and we're going to focus on three different ones. First, there's end behavior. So that's just where does it go when it reaches the ends? Towards negative infinity, towards positive infinity, somewhere else along an asymptote. Where does it go? We're going to talk about local extrema. Those are the maxes and the mins, all throughout the middle of it, in the wiggly bit. And then we're going to talk about the roots and how important those are and what's going on at the different roots in terms of multiplicity and things like that I don't think you've talked about very much in Algebra 3-4. So that's where we're going right now. So let's talk first about end behavior. End behavior depends pretty much exclusively on the leading coefficient, a sub n, and the degree, n, of the function. So if you look at a function where the degree is odd, like x to the third, you have the graph go up on one side and down on the other. This is not an x to the third graph. This is more like a 1, 2, 3, 4, 5, x to the fifth graph, but we'll talk about that in a second. If, say, you had a negative in front of the x to the third or the x to the fifth, say a negative 2 or a negative 8.6, then you would flip the graph upside down. So there's your leading coefficient. If it's negative, your graph is going to go up on the left side and down on the right. But you already knew this. This is just formalizing it for you. If your degree, and when I say degree, I'm talking about n, don't forget that, okay? If the degree is even, that's like x to the fourth or x to the sixth, then that graph is going to go up on both sides, both ends. If the leading coefficient is negative, say f of x equals negative x to the sixth, or negative 2.18 x to the eighth, right? If that degree is even and the leading coefficient is negative, both of the ends go down, okay? These happen to both look a lot like x to the fourth graphs. Again, we'll talk about that in a bit, okay? So this is the leading coefficient, and this is the degree. And that's going to tell you end behavior, even if you don't know anything else. All right, now we know what the ends do. Let's look at what happens at the bumps in the middle, at the local extrema, the maxes and mins. So I'm going to claim that a polynomial will have at most some number of local extrema. And I'm going to say that has something to do with the degree, the n value, the highest exponent. So I want to figure out what that could be. Does it have n local extrema, like the same number as the highest degree? For instance, if it's an x to the third graph, can it have 3 maxes and mins? Or can it only have 2? Or can it only have 1? Like, what's the rule? So, let's look. So here's an example. F of x equals x to the third plus 2. So it takes your x to the third graph and slides it up 2. Does this have any maxes and mins? No. Pretty much here it's going a little bit flat, but it never has the bump up or the bump down that sometimes an x to the third graph does. So this one has 0 maxes and mins, 0 extrema. So let's look at this one. We've got x plus 2, x minus 1, x minus 4. Well, that's an x times x times x to the third graph, right? I just wrote it in factored form because it'd be easier to look at. It's positive, so we know it goes down on this side and up on this side. So let me fill that in. And now I've got to get this graph to go through negative 2, positive 1, and positive 4. So let me fill that in. Okay. Now how many maxes and mins does this graph have? I mean, once I came through negative 2, I had to turn around to get down through 1. So there's one turning point, one maximum right there. And I had to keep going through here. I had to turn around again to get to positive 4. So there's one there. So this has two extrema, one max and one min. Okay, this was an x to the third graph also. So the degree was 3, and I had 2 extrema. All right, let's look at another one. Okay, I was getting a little silly, right? So we have a root at 0, at -5, at -3, +2, +3, and +6. Okay, so it's positive here, and it's got 1, 2, 3, 4, 5, 6. Ooh, this is a degree 6 graph. I know that because this is even, it's going to go up on both sides. So here, make it go up, and here I'm going to make it go up. Okay. Notice this was positive. If it had been negative, they both go down, right? Okay. So going down, I've got to turn around and go through this one. Oh, okay. And turn around and go through this one. Yep. And turn around through this one. Yep. And through this. Oh. And then down. Up. Oh, and it works. Okay. So let's look at the number of extrema. 1. There's a max. 2. There's a min. 3. 4. 5. This has 5 extrema. Okay. So we had an n value of 3 here and 0 extrema. With 3, we could come up with 2. With 6, we came up with 5. n minus 1. Okay? 1 less than the number of the degree. Now, you can have a lot less, but there could be at most n minus 1. Could I have gotten more out of this? If I had one more turning point here, right? If I had one more extreme, it would send this end back down, and suddenly we'd have an odd degree. So I'm claiming this is the most you could get. All right, now for roots. So a polynomial will have at most how many roots? N, n minus 1, n minus 2? Think about it for a second. So this polynomial, it's kind of written very generally with p's and q's and r's, where the p, the q, and the r, and the s, they're all the roots of the polynomial. This is an x to the 1, 2, 3, 4th, so the degree is 4. How many roots does it have? 4, right? Can you have more roots than you can have factors? Right? If I add another factor pair, don't I just increase the number of x's, the degree as well? So I'm going to claim that a polynomial will have at most n roots. Same number as the exponent of the leading term, the highest degree term. Knowing how many zeros there are is one thing, but knowing what the graph does as it crosses through that x-axis at each zero, that's a completely separate issue. So sometimes a graph will pass straight through, sometimes it'll bounce off, sometimes it'll squiggle as it goes through, and knowing what's going on with the multiplicity of the zeros, it's what's going to help you tell what's going on with that graph at that point. So let's look at this for a second. Take the factored form of a function, and again I just have the weird variables in as the places where it crosses, but I've put in some exponents. So this factor is a root at p, and that root, the 0, has a multiplicity of 2. Okay. This root at q has a multiplicity of 5. Right? It's like there are 5 of that root all jammed together into one location. Okay, there are 3 of these, multiplicity 3, and this is multiplicity 1, because there's nothing written there, right? Okay, so let's look at what a graph does if you have, let's just start with the easy one, the multiplicity of 1. So the graph is going to cross through x, well, yeah, it just goes straight on through. Right there, multiplicity 1, straight through. Okay, so this would be like S. What happens if M is even? Well, it behaves kind of like a quadratic. So if this is my root at P, okay, my graph could come in and then go, oh, nope, back out. It's going to bounce off, just like a quadratic would. And x to the fourth and x to the sixth and all of those, it works the same way. Okay, bounces off. Now, it could also just as easily bounce off the other side. It just depends on where the graph was coming from. So what the last root was and where it was after that. Is it coming from the bottom or is it coming from the top? But it'll bounce off if you have an even multiplicity, an even exponent up here. Okay, if M is odd, something like Q or R, you can have the graph behave like an odd degree function. It's going to go up, whoa, and go like that. Or it could do this just as easily. Okay, something like that. We call this point a point of inflection, where the graph has gone from sort of concave up to suddenly concave down. So it's opening up kind of, then it's opening down. There's a point where it goes from one to the other. That's a point of inflection. So we can just say there's some inflection there. That becomes super important in calculus. Right now, not a big, huge deal. Just think straight through, bouncing off, or it has a curve as it goes through.